ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about Zumdahl, the 7th edition. The book's named Chemistry, and we're in chapter 8 now. So this is all about bonding and its general concept, so it's not anything too particular. But to start with, what are our focus questions for this chapter? So questions to consider. The first thing is, what is meant by the term chemical bond? So in other words, what exactly is a bond? Why do atoms bond with each other to form compounds? Generally speaking, most people would probably think, oh, well, why do molecules form? Why aren't we just, atoms bouncing around and that's it? Like, what is the driving force for forming something like a compound? How do atoms bond with each other in order to form these compounds? Those three questions are kind of what are going to be driving us through this chapter. So let's start with some types of chemical bonds and exactly what that means. So the first thing is, what is a chemical bond? There's no simple, complete way to define a chemical bond. You might think it's super easy, and it's really not. But what do you need to know? And how exactly do we define it for like the AP exam? Okay, so the first thing that you need to generally be aware of about chemical bonds are that chemical bonds are forces that hold groups of atoms together, and that forces them to function as a unit. So it's kind of like hitching two train cars to each other, or if you're towing something. The bond is like the link cable between both of them. Now they're traveling as a unit, okay? And now they act as if they are a unit. Now, a bond will form if the energy of the compound is lower than that of separated atoms. Atoms by themselves have a particular amount of energy, and then when you bring them close together, in some cases, the energy can actually be lowered, the potential energy. And if it can, then a bond will naturally form. So the driving force of forming a bond is energy. And the lower the potential energy, if you can lower the potential energy of the system, then of course, a bond will just form. So a good way of visualizing this is kind of in this diagram. So if you have two hydrogen atoms, I have a hydrogen atom here, hydrogen atom here. Again, notice that we have a plus representing the proton in the center. And then all of these little dots, the dots themselves are just representing the locations that the electron, because remember, hydrogen atoms only have one electron, but the possible locations of where that single electron might be at some point in time. So if the hydrogen atoms are sufficiently far apart, they don't even interact with each other at all, right? If I have a hydrogen atom here and I am infinitely far away and have another hydrogen atom, there's no force of attraction between the two. So there's really no interaction at all. But let's say I now bring these infinitely far apart hydrogen atoms closer and closer together. The closer they get, the more they start to interact with one another. And then eventually what you'll find is there is an optimum distance to lower the overall energy of the system. So believe it or not, these hydrogen atoms by themselves have a particular amount of energy, but as they get brought closer and closer together, it will lower the overall energy of both of the hydrogen atoms. And when it does that, that is the optimum distance and a bond will form, okay? And there is a good way of being able to visualize this using a potential energy graph. So the potential energy graph that I have here shows two hydrogen atoms. And so you have this like imaginary little zero marker here. And this would be like zero potential energy measured in kilojoules per mole. And so you can picture that if your two hydrogen atoms are infinitely far apart, you're basically touching this 0 point on the graph, okay? As you get infinitely further and further and further away from your two hydrogen atoms, right? Now, as you bring them closer and closer, what you can see is that they begin to interact with each other. And as they interact, the potential energy starts to go down. And there is a trough, kind of a minimum point where that occurs. And the point at which that occurs is when a bond will actually form between your two hydrogen atoms. Now notice that if you keep pushing them closer and closer and closer together, instead of being, attracted to one another, they become repulsive, and instead you start to get this gigantic increase in potential energy, because now you're basically putting two hydrogen atoms on top of each other, okay? And a good kind of demonstration of that uses a simulation, a PhET simulation called atomic interactions. So what I'm going to do is I'm going to zoom in real quick. And so let's say we have two neon atoms here. You can see that if I move them infinitely far apart, I have basically, no attraction. But if I bring them close enough, you can see that on its own, it is attracted, and that form of attraction is going to bring it closer and closer and closer. And then notice that it got repulsed and moved away, but now it is just still attracted, and it's going to keep going further and further closer and closer and closer again. And eventually, when you get to that trough point, like right here, this is pretty close, it has the lowest energy, and so it will form a bond. So now these two neon atoms are bonded together, okay? Now there are a couple of important things that you'll notice. So this is for neon. Look what happens when I change it to argon. That trough is a lot deeper, which means that the potential energy is a lot lower. And look when I put two oxygen together, it gets even lower. Okay, so what exactly does this potential energy stuff kind of tell us? And not only that, you can probably also see, look at the distance between here and here. That changes also with each element that I'm putting together. So what's going on with regards to that? Well, you can see here, this is the internuclear distance right here. And so what you can think of that as is how close are your atoms to each other. And so if we go back here, okay, and we compare them, oxygen has its atoms a lot closer together. There's a bigger overlap than there is for argon or neon, okay? Something else that you'll notice is that there is a huge difference in potential energy when you get to oxygen here, and that's because the bond is a lot stronger. In fact, it's a double bond, and so we'll talk about that eventually. But that's kind of the point of what you can utilize this graph to represent. Okay, so let's go back. And again, you can mark this then as a high repulsion area. This is no attraction, and this is where we have our lowest potential energy on our graph. Key ideas. First things first, what kind of bonds are there? Okay, first we have ionic bonding. So ionic bonds are bonds where electrons are transferred, okay? And this happens between metals and nonmetals. So right here I have my sodium, and right here I have a chlorine atom, and you can see that I have one valence electron for my sodium. I have an empty space here for this halogen. So for the chlorine atom, it doesn't have 8 electrons in its outer shell here. It has a space to actually have one right here. And so it will very readily take the electron from our sodium, and sodium will now have a plus charge. And now that electron's been transferred to the chlorine, it now becomes chloride, and that has a negative charge. And so now these two things are hooked together. We have a positively charged ion, a cation, and we have a negatively charged ion called an anion. And now, because we have a positive and a negative, they are attracted to one another, and they form a unit, which we call an ionic compound. And so right here, we have an ionic bond that is forming. Now, what about covalent bonding then, right? So we know that these are opposites, but covalent bonding is when electrons are shared equally by the nuclei. And this only happens with two of the exact same nonmetal. So again, the two hydrogens that we utilized in our first example, or in our PhET simulation, the two neon or the two argon or the two oxygen atoms. Now, here's the thing about this. Ionic bonding and covalent bonding are great, let's say, philosophical ideas, okay? And so we like to categorize things into two categories, ionic bonds or covalent bonds. But in reality, there are intermediate cases. And that's when we get some very interesting things, okay? So again, if it's a metal and a non-metal, there we go. We have an ionic bond. Everybody knows that. When we have two of the exact same non-metal, like two hydrogens or two oxygens or two nitrogens, those are covalent bonds. But what happens in the intermediate cases? And so we call those polar covalent bonds. And so what ends up happening is this. There is an unequal sharing of electrons between the atoms in a molecule. So when we have two hydrogens or two oxygens or two nitrogens, the sharing is pretty unanimous. Both are being shared equally. All right. But what if we have two different nonmetals? In that case, you might think, oh yeah, they share electrons. That's what a covalent bond is all about. And they do, but they don't share them equally. One atom is better at stealing and taking electrons than the other one is. So instead, the electrons will spend more time around one of the atoms and less time around the other atom. And so what this results in is a charge separation, and it leads to partial positive and partial negative charges. And so the way that we like to represent those, and you can see this with water. Water is polar, and it's made up of polar covalent bonds. This hydrogen here, and this hydrogen here, they do not get to have the same pool of electrons as the oxygen does. And so the hydrogens here are basically donating and sharing their single electron with this oxygen. And this hydrogen is also doing the exact same thing. And the oxygen, is sharing its electrons, let's say, but definitely not equally. The oxygen is much, much better at keeping the electrons around itself and keeping those electrons away from the hydrogens. And so what we like to utilize when we're talking about polar covalent bonds and polar covalent compounds is we use this Greek symbol. It's a lowercase d or a lowercase delta with a little positive sign. And so there's going to be a partial positive part of a water and a partial negative part of the water. So the partial positive part is going to be the part of the water molecule in this situation that doesn't get to spend as much time with the electrons. And in that case, those would be the hydrogens. The hydrogens have a partial positive charge. The oxygen, on the other hand, is better at keeping electrons, and so it's going to have a partial negative charge. And you might think to yourself, that does sound familiar, and it should. It should kind of sound familiar to you, and I'll tell you why in a couple of slides. So now, what about these partial positive and partial negative charges, and how exactly can we picture them? So partial positive and partial negative are exactly what I just said. It's, indicates a positive or negative fractional charge. So unlike, a cation or an anion, which has a plus or a minus, or a +2 and a -2, these are very, very slight positive or very, very slight negative charges. We're talking about fractions. And so you can see that if we have hydrogen and fluorine and we put them together to make hydrogen fluoride, the hydrogen is not going to be as good at, again, keeping electrons, whereas the fluoride part of it will keep onto those electrons. And so if you have these two pieces of metal, and you decide to put an electric charge through them, what you'll see is that all of the molecules start to line up so that the partial positive charges are facing the negatively charged metal panel, and the partial negative charged fluorides are going to face the positively charged panel. But normally, if there's no electric field going through there, they just bounce around and do nothing. But if you start to apply an electrical field, you'll actually see that if something is polar covalent, you'll start to see them line up with the negative part of their molecule facing the positively charged plate, and the partial positively charged part of their molecules facing the negatively charged plate. And so what is meant by the term chemical bond? So let's go through our key items now. So it is difficult to describe, but it describes how atoms kind of function as a unit when they hook together. Okay? Why do atoms bond with each other? Well, they bond in order to lower the amount of potential energy of the system. How do atoms bond with each other? Well, they bond either by sharing their electrons in a covalent bond or by transferring electrons in an ionic bond. But a lot of what we're going to be talking about is actually somewhere in between. Okay, and so now hopefully this stuff sounds familiar. And why are some atoms better at attracting electrons to themselves than others? And that is a periodic trend that we already talked about called electronegativity. So electronegativity is the ability for an atom or in a molecule to attract electrons to itself. And the pattern from the periodic table is this: that as you go across the periodic table towards fluorine, you get more electronegative. As you go down a group, you become less electronegative. And for the most part, our noble gases are an exception to that because they don't really form compounds for the most part. Okay? And so notice that pattern is fairly consistent as we go across. So how exactly does electronegativity work, and how does it relate to bond type? So here's kind of our difference. And is there a hard number associated with this? Because if we go back, you can see that there are numbers here, right? Like you can measure the electronegativity. And so right here for fluorine, it's 3.98, and for hydrogen, it's 2.20. So is there a way of, basically using math to figure out, like, okay, is this polar covalent? Is it covalent? Is it ionic? What is it exactly, by comparing these values to each other? Some books say yes, there is like a cutoff for what makes something polar covalent versus ionic. But for the most part, it's kind of a sliding scale. So if there is zero difference in electronegativity, the bond type is purely covalent. On the other hand, if you have a very large difference between the two electronegativities, then you have more of an ionic bond between the two, because then you're more likely to have one of the elements just kind of steal or take the electron completely from the other atom. And then you have the intermediate, polar covalent, which is, again, somewhere in between the two. And again, there's a really good PhET simulation. I love PhET simulations that kind of shows that. So right here, you can see that we have a sliding scale of more covalent and more ionic. Well, look, the electronegativity of both of these is exactly the same. But look what happens when I start to move and make atom A be more electronegative. Eventually, when I have something that has so little electronegativity, something that has so much electronegativity, you virtually have an ionic bond at that point. Okay? But again, if they have the exact same electronegativity, then they are completely covalent. Most bonds that we discuss, especially in this unit, are somewhere in between covalent and ionic, which makes them, you guessed it, polar covalent. Notice what happens, though, as I keep sliding more and more up. You can see that these partial charges start to appear. This would be, since it is the less electronegative of the two, more positive. This, because it is more electronegative, the yellow one, is going to be more partially negative. And that makes sense, or should make sense to you, because obviously if you are better at sharing and taking electrons from something, then of course the electrons are going to spend more time around you and you're going to be partially negative. Whereas the less electronegative one here, it's going to not have that ability. And the cool thing is, if we do, apply an electric field or something, you can see that flipping around, because now look, this has a positive charge, this is a partial negative. So of course, the negative part is going to try to face the positive plate. Of course, the partially positive part is going to try to face the negative plate. And again, it's just a really good simulation. Now, let's arrange the following bonds from the most to least polar then, okay? And if you need a copy of the electronegativity chart, feel free, but notice that there's a pattern here. Okay, so let's put the first ones, a nitrogen fluorine bond, an oxygen fluorine bond, or a carbon fluorine bond. Okay, what do they all have in common? Well, they're all right here. Okay, so if I'm looking at electronegativities, carbon has the smallest electronegativity, then nitrogen, then oxygen. So if I'm putting them from most to least polar, then the one with the biggest difference, so the carbon-fluorine bond is going to be more polar than the oxygen-fluorine bond because they're a lot closer in electronegativity. What about this? Carbon and fluorine, nitrogen and oxygen, silicon and fluorine. So again, I have carbon and fluorine, I have nitrogen and oxygen, and then I have silicon and fluorine. So again, if you're just looking at even the colors on the chart, the first one, which has the biggest difference, would be silicon and fluorine, then carbon and fluorine, and then nitrogen and oxygen are right next to each other. So they're going to have the least polar bond possible. And then you can repeat yourself for this one. So we have ClCl, so chlorine and chlorine. That would have an overall electronegativity, an electronegativity of 0 then at that point, right? So that would be purely covalent. And so, of course, that's going to have the least polarity because it's going to have a polarity of 0. Boron and chlorine. So we have boron and chlorine. Okay, that's a pretty big difference. And then we have sulfur and chlorine, which are right next to each other. Okay, so again, just even without the chart, if you didn't have the colors, you'd be able to tell based on the electronegativity pattern. Which of the following bonds would be the least polar, yet still be considered polar covalent? This is actually a really good question. So take a look and see if you can think through, using our electronegativity chart here, which one you think it would be. Answer: nitrogen and oxygen. So they're clearly different from one another. If you tried oxygen and oxygen, that wouldn't work because that would be purely covalent. And if you tried magnesium oxygen, that's a metal and a non-metal. And so that's the biggest difference, of course, that you can get, but that's probably an ionic bond. So now I'm getting ahead of myself. Which one would be the ionic bond? There we go. Magnesium and oxygen, we have a metal and a non-metal. Which one would be fully covalent? That one should be pretty obvious. If you have the exact same element bonded to itself, that must be a purely covalent bond. Which would be the most polar without being considered ionic? Again, it's the one with the largest difference. So silicon and oxygen versus carbon and oxygen. Well, silicon and oxygen is going to be, again, the most polar. But again, silicon is a metalloid, not even a metal, and oxygen, again, is a non-metal. Bond polarity and dipole moments. All right, so again, dipole moment, very important. It is a property of a molecule whose charge distribution can be represented by a center of positive charge and a center of negative charge. And so we like to use an arrow to represent dipole moment, and the point to the negative charge is the center of the tail of the arrow, indicating the positive center of the charge. So in other words, in this picture, we draw a little arrow, and the arrow kind of has a little cross. And so the tail of the arrow is going to be our center of positive charge, and the direction the arrow is pointing, so the arrowhead itself, that's going to be our negative part. Okay, so again, there are multiple ways of drawing and depicting dipole moments. This one in the middle is the most common, but you can also just put a delta positive on the side or a delta negative on the side. Of which part would be your positively charged area and which part would be your negatively charged area. You can also use this electron density map, which sometimes you'll see. The bluer something is, the more positive. The redder something is, the more negative it is. Now, what if there's no net dipole moment? Well, in that situation, if you have electrons being pulled this way, but also electrons being pulled this way, then that means that in general, your dipole moments are canceling each other out. So you actually have this net of basically a polarity of 0 right around your carbons because they're being equally pulled in both directions. And so your oxygen, on the other hand, here still have their electrons around them and still have that electronegativity there. So you can see there's still red, but you have this huge section of blue right in the middle because the dipole moments effectively cancel each other out. And again, good old PhET simulation stuff. It can be very easily shown. Again, let's start with all of them having the same electronegativity. So all of them have the same electronegativity. They're not polar or non-polar. There's no such thing because all of them are the same atom. Okay, but what if I make that pole symmetrical, and now I make one of these really, really negative, and I make the other one also really, really negative. Okay, well, now I have a dipole moment where everything is getting pulled into the middle. Okay, so this one right here becomes the most negative possible, whereas these become, positive, partially positive, because now they no longer have really the ability to take electrons from anything. They have such a low electronegativity. Well, what if I do the opposite? So what if I make that one on this side really, really electronegative, and I make this one over here really, really electronegative? Well, again, in this situation, now I have something where I have negatively charged things on the outside, but a positively charged thing right here in the middle. And if, I make it really, really bad, this central atom, at attracting electrons to itself, look what happens. You can see even the greater disparity. What if I make them all the same again? Notice there's no dipole moment at all anymore. And yes, the shape of your molecule does make a difference. Spoiler alert, we'll deal with that later on. So for now, you don't need to worry about that, but we will be dealing with it later on. Now, what about section 8.4, ions and electron configurations and sizes and stuff like this? So now we're talking about stability, right? So why exactly do particular atoms form ions and others really don't, right? Because again, we're talking about ionic bonds to some degree, right? And so in order to form an ionic bond, you need a cation and you need an anion. So atoms, generally speaking, form compounds because when they form a compound, that allows them to have a noble gas electron configuration. So here are our electron configurations for the noble gases. Helium is boring, okay, but neon, pretty interesting, argon, krypton, xenon, radon, etc. So what you'll notice, right, like coming across, is that generally speaking, there is a pattern to them. Let's just say that. And so when two nonmetals react to form a covalent bond, they share electrons. And so when they share those electrons, they complete the valence electron configurations of both atoms. And that's, again, a stabilizing force. Now, when a nonmetal and a group metal react, they form ionic compounds because, again, when you form ions, the valence electron configurations of the nonmetal basically becomes the electron configuration of a noble gas. And normally, for a main group metal, the valence orbitals of the metal are totally and completely emptied. And when that happens, a lot of them actually form also an electron configuration that's like a noble gas. And so what that means is that we have what's called an isoelectronic possibility for multiple elements on the periodic table and ions. And so an isoelectronic series is merely a list of ions and atoms that contain the same number of electrons and are totally stable. So here are all different ions. In this case, you have an O2 minus, so that's an oxide ion. You have an F minus, that's a fluoride ion. You have neon, which is just an atom. You have a sodium ion, a magnesium ion, and an aluminum ion. All of them have the exact same electron configuration. And again, think all the way back to when we talked about electron configurations. Okay, think back to that last chapter. All right. Remember that every element on the periodic table, every stable element on the periodic table has an electron configuration. And then we also said, hey, we can also do this for ions. But when we form positive ions like sodium here and magnesium and aluminum, they have lost electrons. And when they lose electrons, now in that situation right here, they have a noble gas configuration. This is the noble gas configuration of neon. On the other hand, these ones, the negatively charged ions, the anions, they gain electrons, and that props them up to also having the same exact electron configuration as a noble gas, in this case, neon. And so this is another reason why these ions form, because then they end up with, in this case, emptied shells, which gives them an electron configuration that is similar to a noble gas. And that's for positive ions. But for the negative ions, they gain electrons, which again fills in empty spaces in these valence electron shells, which gives them the electron configuration of a noble gas. And again, it's pretty obvious when we look at the periodic table. Oxygen just needs 2 more electrons in order to get its noble gas configuration. So guess what it does? It gains 2 electrons to give itself a -2 charge. Fluorine only needs 1 extra electron to get to neon. Guess what? It does the same thing. Sodium has 1 too many. So it gets rid of its electron to have a positive charge, and now you have, an electron configuration similar to neon. Magnesium has 2 extra electrons, and so it will get rid of both. And then even aluminum will get rid of 3 electrons in order to get its neon electron configuration. All right, well, that takes us to the halfway point. Again, thank you very much for listening. If you guys could do me a favor, please like and subscribe to the channel. I will continue with chapter 8. It is a little in depth, so I'll get that posted as soon as I can. And thank you for watching.